在物理研究所研究员、博士生导师郝芬教授给我们讲他最近的工作。郝老师他主要从事量子可及模型的研究，近年来聚焦于量子信息与高能物理的前沿领域中的新型物理模型的可及性问题，为理论物理专业研究生讲授高等量子力学、量子场论等课程。本科毕业于西北大学物理学基地外，期间作为交换生赴南京大学学习，随后被推荐至西北大学现代物理研究所攻读硕博连读学位。2013年获博士学位并留校任教，曾获陕西省优秀博士学位论文奖以及陕西省人才计划项目支持。2015年赴美国布鲁克海伦国家实验室访学，后以 Rainbow Visiting Fellowship 访问澳大利亚昆士兰大学。2018年至2021年，在美国纽约州立大学史蒂芬教杨振宁研究所从事博士后研究，在本领域权威期刊如 J-Ham、Physical Review 系列、Nuclear Physics、Annals of Physics 等发表论文50余篇，主持国家自然科学基金项目4项，省级自然科学基金项目1项，作为国家自然科学基金委彭桓高能基础理论研究中心陕西省理论物理前沿重点实验室团队骨干成员，参与多项国家级重大科研项目，欢迎。
忘了介绍，然后我用英语用看。
随便你。有外国人还有英语课吗？
Okay, first, I should thank Professor Wang for inviting me and for giving me this chance to give this talk to present our recent work. It's about frustration-free spin chain, and this work is mainly partly based on this short notes we put on arXiv earlier this year, and it's mainly about some ongoing work with 3 Indian guys. They are Akash Sinha, Vivek, Kumar Singh, Pramod Panamanabahan. They come from Institute of Indian Technology, and a senior professor, Vladimir Korykin from Stony Brook University. Okay, then I will introduce a frustration-free chain, and it has non-invertible symmetry, and I will mainly focus on the model with duality. First, let's review the Wegener's theorem in quantum mechanics. So it says that for ordinary system, the ordinary global symmetry are performed by this unitary or invertible operators. But for non-invertible operators, since they lack inverse, they do not form groups, but they can form some kind of closed structures like algebra. So our model is such kind of instance. Before we proceed, I would like to take transverse field Ising model as an example to illustrate our model. Here, capital X and capital Z are the ordinary polymatrices with subscript J, means acting on the J's site or lattice quantum lattice site. And for this transverse field Ising model, it has the symmetry like Z2 spin flip symmetry and also this translation invariant translation symmetry. So this Z2 symmetry will not change sigma x, but will give this sigma z a minus sign. And the translation symmetry will shift the system, whole system to the right by one side. And then there's this famous Kramers-Wiener transformation. It can map, roughly speaking, map x direction to z, and then map z to x. And the model has this duality under this transformation. It can map hj to h1 origin. And such a transformation is realized by this non-invertible operator in this form.
What
Uh,
is
H.
the algebra?
You mean this calligraphy H? H. Okay, this is just the Hamiltonian. In order to distinguish later, I will also use capital H.
Literally, this kind of font is used for the algebras.
Yes, yeah. This used by my co-author since we want to distinguish this from later we will use the standard Hamiltonian H. This is kind of a case of Indian guy. Okay, then this operator D together with this Z2 and the translation operator U and T, they do not form a group, they form a closed algebra. Then our target is to introduce a class of frustration-free swing chain with the nearest neighbor interaction and with non-invertible symmetry. And they have this local Hamiltonian described by two real number as parameters. And the system has zero energy as ground state energy and has corresponding eigenvectors. And since it's a frustration-free chain, so this means that the global ground state are the combinations of the local ground states, each local ground states for the local Hamiltonian. Then the ground states also twofold degenerate, and they are not entangled. And this twofold degenerate can be related to each other, can be mapped to each other by this non-invertible symmetry. And such a symmetry will be broken in the thermodynamic limit. And also the spectrum of this Hamiltonian is gapped. Okay, here we formally introduce our Hamiltonian in this form. It's a series of local nearest neighbor interaction sum over together, and here we use a periodical boundary condition. Here, capital A and capital F are projectors, isomorphic projectors. They have the same structure, and the structure of A is like this. So the elements of the first row are 1 and A. Then the second row elements are A and A squared. This means that the second row is A times the first row. And similarly, the second column can also be seen as A times the first column. And then this fraction in the front is used to normalize this matrix to make sure it's a projector. So square A will return back to itself. And F have a similar structure. So simply by replace the parameter small a, we will obtain capital F projector. And both A and F operators have eigenvalues 0 and 1, and their corresponding eigenvectors we mark as cat 0 and cat 1. And then this tensor product AJ, FJ is a rank 1 projector. This is just a local Hamiltonian term. And they are projected onto this 2-qubit Hilbert space to this state.
What is rank 1?
Rank 1 means that it's degenerate. Yeah. So only as a, for example, like this one, if you calculate the determinant, it's 0, right? Yeah, rank matrix. Yes. And then the global ground state are the tensor products of the local ones, local tensor products, cat 0, A cat 0, F, and also have this 0 energy ground state energy. And this twofold ground state can be mapped to each other by this non-invertible operator SA or SF. They are a series of products of A perpendicular and F perpendicular local operators. These two are the pseudo-inverse operator of capital A and capital F, since they are non-invertible, and I will show the definition in next frame. And this SA and SF, they commute with the Hamiltonian, so they are the symmetries of the system. And then in the thermodynamic limit, such symmetry will be broken. And here we show the definitions of A perpendicular and F perpendicular. So basically, they just swap the diagonal terms and then give the off-diagonal terms a minus sign. Similar, we have this fraction in front to normalize. And then the fusion rules of A perpendicular and F perpendicular will give rise to this new operator U after we get rid of the diagonal terms. Then this U is the invertible operator, and it has Z2 symmetry. This is a local one, and then the global symmetries and this duality, like small u, here capital U, are the tensor products of the local operators. And then we are mainly interested in the Hamiltonian with duality term. Here we introduce the dual term. G is a coupling constant, and HFA is just this HF by swapping their parameters. And then for G is greater than or equal to 0, this twofold ground state structure does not change, still twofold degenerate. And then this U operator will realize the duality for this model. It can map Hj to H1 over G. And the square of U is identity, so it's a Z2 operator. Here we give some comparison of the transverse field Ising model and this AF model. So they both have duality and symmetry properties. For the Ising model, the duality are realized by this non-invertible operator D, and its symmetry is related to the invertible Z2 spin flip operator U. And then for our AF projector models, actually it's a class of, can be generalized, so I say class of. Here, the basic one is that its duality realized by this Z2 operator U as we just introduced, and then its symmetry are related to this non-invertible operator D can be chosen as like SA or SF. They are just the products of local A perpendicular F, which are the pseudo inverse of the original capital A and capital F operators. And then let's return back to this pure HAF model without the duality term. Then according to Bravi-Gossett theorem, in their paper, they gave some criteria to determine whether such a nearest neighbor system is, its spectrum is gapped or not, gapped or gapless. So
what is this matrix C? Is it transformed?
You mean this matrix? Yeah, this matrix is introduced by them. So this is a ground state and the first excited state, like 0 and 1, which we introduced previously. It was here. Good. 0 and 1, cat 0.
What's the physical meaning of this matrix? Is it transfer matrix?
Not a transfer matrix, but
And then why its eigenvalues to tell whether it's scattered?
actually, I'm not familiar with this detail. So, but we used their criterion, directly use their results and evaluate whether our system is gapped or not. And then we do some numerics, and it confirmed that it does describe. Also can be applied to our case.
So what is the phi?
Phi is the projector which is composed of this local Hamiltonian density AF, which we introduced previous here. Yeah. This state, yeah. So the Hamiltonian density is a projector onto this state. So that's the point. So here we directly used their results, evaluate the matrix composed of this inner product, which are this phi state with the ground state and the first excited state, local ones, and compare the two eigenvalues of this matrix, and we conclude that according to them, our system should be gapped. And means when in the thermodynamic limit, when n tends to infinity, there's still some space between the ground state and the first excited states. If it's gapless, then the first excited states will approach the ground state. They will merge together. Yeah, that's a gap. Okay. What? Sorry.
How large is the gap?
Sorry.
How large is the gap?
How large? Yeah, it depends on the parameter choice. Yeah, but still it's gapped. Depends on how large we choose A and F. Yeah. So here in this three.
In thermodynamic, the gap should be independent of the system size.
Yes. So here we show some numerical results on testing whether the system is gapped or not with different parameter A and F choices. And here we show the results up to total lattice size n is 14 lattice size. Actually, we have the results of total lattice size n up to 80 by using DMRG algorithm, but we didn't show them here. So, but generally, the numerical results confirmed the gapped spectrum analysis come from Bravi-Gosset theorem. Okay, then there's the main part of my talk. We are mainly interested in the AF model with duality. So especially at a special point, J is equal to -1. So in this case, the duality operator U will become chirality operator. So it maps Hj -1 to -Hj -1. So right now the Hamiltonian is a following local form. It's just in terms of the global ones, HAF, the original AF minus HFA. If in terms of local ones, it has this format. Then if we impose this periodic boundary condition for n is to 2 case, then the Hamiltonian has this form. It's H12 plus H21 swept space. And in terms of local projectors, it's A1 F2 minus F1 A2 plus A2 F1 minus F2 A1. Then here this A2 F1 will cancel F1 A2. Also this A2 F2A1 will also cancel this A1 F2. So this will lead to an all zero elements matrix. Then from another point of view, if we write down the matrix form of this local Hamiltonian density H12 and H21, we have these two matrices. So except this OR factor, which can be taken out of the whole matrix, then the remaining matrix has this form. So compare the two, we observe that these two matrix elements have the opposite signs on their corresponding matrix elements. So they will, if we add them together, they will completely cancel each other. Then if we come to n is equal to 3 case, the Hamiltonian has this form. Still, it has this overall factor, and yeah, for n is equal to 2 case, all the Hamiltonian elements are cancelled, and for n is equal to 3 case, such cancellation will have a staggered behavior, so they will don't match each other completely. So means that they will not cancel each other completely. Then we're leaving some remaining elements in this Hamiltonian matrix form. So in this case, this Hamiltonian has this overall factor which can be taken out, and the remaining matrix has this form. So this matrix is composed of 3 cancel elements, 0, 1, and then -1. And also here, in each column and each row, 1 and -1, they appear in turns, in their sign in an alternating way. So like 1 -1, then 1 -1. So such a pattern immediately reminds us the alternating sign matrices in combinatorics. But there's some difference. So for a standard alternating sign matrix in combinatorics, the numbers of 1 or ones and the number of -1, they are not the same. So the numbers of ones in each row and column has one more than the numbers of -1s. And also for each row and column, the sum over, so in this case, so the sum over over each row and column of a standard alternating sign matrix is 1. Since the 1 has one more, the number of 1 is one more than the number of -1, and also alternating way. And also in the standard alternating sign matrix, in each row and column, only +1 can start or end a row or a column for the non-zero entries. But for our case here, 1 and -1 appear in pairs, so they will cancel each other out. So in each row and each column, we can either start with 1 or -1, and the sum over each row or column are all 0. In the standard one, the sum over each row and column are 1. And also, okay, there are more symmetries in this matrix. So means that HJK is HKJ. So the transpose of this matrix is itself. And also another antisymmetric, HJK is minus H sub 2 raised to n minus j plus 1 and 2 raised to n minus k plus 1 means that the up left is antisymmetric compared with the lower right, means that if we flip this flip over along the anti-diagonal, it will give a minus sign. And then if we throw away this overall factor, then the eigenvalues of the remaining matrix also have this symmetric form. then the similar pattern will happen for larger lattice sets. Even can be large to infinity, so the same pattern. Then have the same overall factor which can be thrown away. Here, this factor is the same as here. So, and then the remaining matrices are all composed of 0, 1, and -1, still alternating sign pattern, and the similar symmetry as we discussed in last frame, and then also a lot of symmetries among the eigenvalues of this remaining matrix. And then let's discuss the standard alternating sign matrix a little bit. So there is a theorem. It's about the number of the n by n alternating sign matrices. So means that the number of such kind of matrix has this factorial expression. It was first conjectured, then proved by different people from different points of view. Now it's a theorem. So then it says that for the first like n is equal to 1, 2, 3 cases, the total alternating sign matrices numbers are 1, 2, and 7, etc. Here we list all the alternating sign matrices for the n by n up to 3 cases. So 3 by 3 cases. So for the standard 1 by 1 alternating sign matrix, it's simply 1. So since we require the sum over each row and column should be 1. So only 1 is allowed. And then for the 2 by 2 alternating sign matrices, they are just the standard identity and the poly X. And then for the 3 by 3 alternating sign matrices, then we have the identity operator and also this anti-diagonal operator. And also we have 4 another matrices looks like lowering or raising operators for the SU3 cases. And then for the last one, the 7th one, we have this is the first time that -1 appeared in such matrices. Then we have, as I said, -1 cannot start or end a row or column. So we have a -1 in the middle, and we have 4 +1s around it. So still the sum over each row and column is 1. And the number of ones in this row is 2, and the number of -1 is 1. So 2 is 1 more than 1. Then let's return back to our case. For the 1 by 1 cases, for the 1 by 1 case, sorry, I forgot to mention that in our case, we also have all zero columns and rows. And for standard alternating sign matrix, this is not allowed. Since for the sum over each row and column, we should give rise to 0. So this is kind of equivalent. Each one and the -1 will balance with each other. So in our case, if we allow all 0 row and column, we have this 0 as 1 by 1 matrix. If we do not allow all zero row and column, then we do not have this 1 by 1 matrix in our current case. And then for the 2 by 2 cases, for the 2 by 2 case, we have this identity and also sigma x, and with the rest elements being -1, 2 cases. And then if we allow all 0 matrix, we also have this 2 by 2 0. And then for 3 by 3, altogether we actually have 33 matrices. Then let me briefly explain these patterns. Then the first category is the all zero matrix, and then we have 18 matrices in this form. These three together with this altogether 18 of them. So they are just this 2 by 2 matrices being embedded into the larger 3 by 3 matrices in different ways. Then even if we do not allow this all zero row or column, then we still have 12 of them. So all these 12 are the real alternating side pattern matrices in our case. So this means that in our case, it seems that the pattern is more complicated than the standard alternating side matrix. So right now, let's stop talking about discussing this alternating side pattern. Okay, now let's return to the Hamiltonian family Hg with a coupling constant duality term AF plus GFA. Then this projectors A and F can be expressed in terms of polymatrices here. This is the identity and X and poly V. And then the F projector can be obtained by replace the parameter A by F. And if we impose paired boundary condition, then at J is equal to -1 case, after we get rid of some diagonal or some constant term, we will arrive at this equivalent Hamiltonian density with nearest neighbor interaction xz minus zx. And also this capital J is the overall factor which we mentioned in the matrix form. And then let's apply a rotation on this matrix on this Hamiltonian form. Along this rotation along the x-axis, so it will transform z direction to y direction. But since it's along x, so it does not change x. So such a global rotation is actually a similarity transformation. So it does not change the eigenvalue or spectrum of the whole system. So after the transformation, the Hamiltonian becomes this form. It's J times sum over x, capital X, y minus yx. So please keep in mind this Hamiltonian. Right now we call it Carroll xi. XX spin chain model. Since here we have a minus sign, and this Hamiltonian has the same spectrum compared with the original one. So here I marked it as blue. Later I will prove that the integrability of such a Hamiltonian can be constructed in the sense of Yang-Bak's algebra integrability. And then further based on this Hamiltonian, we further make a global sequential helical rotation. Means that the rotation on each set are different. So means that at each set the rotation has minus I pi over 4 more than the rotation on the previous one. So here, this J labels the lattice sites of this site in the whole system. Then this global rotation is still a similarity transformation, so it still does not change the spectrum of the Hamiltonian. Then, after some calculation, we arrive at the final expression. Here we have the standard x-axis spin chain bulk term with some additional boundary terms. So right now it looks like some preformings, but not a standard one. Then let's observe the boundary term here. I give the explicit expression for the boundary term. Then we can observe from this boundary term that since the inner bulk is already a standard x-axis chain, then if the total lattice size capital N is a multiple of 4, then such a chain, such a model will become equivalent with the standard x-axis spin chain with periodical boundary condition. But if N is even but not a multiple of 4, like should not be 2, since like I said, when N is equal to 2, all the Hamiltonian will cancel. For example, N is 6 or 10, then such a Hamiltonian will become equivalent to the x-axis spin chain with anti-periodical boundary conditions. And then another cases are the total lattice size N is odd number. Then in that case, this boundary will become some exotic twisted boundary. We do not know what it is. But later I will show the integrability from another point of view, Yang-Bak's point of view. Then let's return back to the integrability of this chiral x-axis chain, which I highlighted, marked as blue ones. It's y minus yx. So it's for this Hamiltonian form, its integrability can be related to the asymmetric simple exclusion process model. And actually, this can be related to another project recently I've been working on, which is in collaboration with Satoshi Nawata in here, and Ji Rui Guo from Tongji University and Rui Dongzhu from Suzhou University. So here I will give some basic setting of this asymmetric simple exclusion process. So it's a Markov process which describes the particles hopping on a one-dimensional chain, and on the chain there are a series of vacancies, and for each vacancy, only one particle can stay on one vacancy or on one site at one time. Then for each site or vacancy, it can have two kinds of status. So either it's occupied or it's empty. Then for an occupied site, the particle on it can randomly jump or hopping to the left or to the right with different probabilities, like jump to the left with probability t and jump to the right with probability 1. Then for the open boundary case, the chain is coupled to an external field. Then there are some particles from the external environment that will arrive at the leftmost first site with probability alpha, and will leave this site with probability gamma. And similarly for the rightmost else site, the particle will arrive with probability delta and will leave this with probability beta. And ordinary people mainly interested in this kind of open boundary cases, since it will provide some complicated physical phase transformation, something like that. And then for the periodical asymmetric simple short for ASAP model. For the paradoxical case, for the chain with certain length and with certain particles, in this circle, the system will automatically have a current, have a conserved current. So its integrable is confirmed from different points of view. Still, similarly, it has the probability jump to the left with probability t and jump to the right with probability 1. And for the open boundary cases, if we require it to be quantum integrability, then we should impose some constraint relation to the open boundaries. But that's not the point which we plan to discuss today. Then such a model, so such a physical model, for the bulk of the open boundary case, also for the periodical boundary asymmetric simple exclusion process, we have this corresponding R matrix has this form. This is a very special R matrix. Here in the previous slide, here T has a physical meaning of probability, but in here T is a crossing parameter in the sense of Yang-Baxter algebra, and X is a standard spectrum parameter. And when this T tends to 0, such a 6-vertex R matrix will reduce to 5-vertex R matrix. Then in that case, it's called here, this point will be missing. So that means the crossing unitarity of such deformation is quite special. And such a R matrix satisfies the Yang-Baxter equation R12, R13, R23, and the relation among the spectral parameters are multiplicative. So here we should use x1 divided by x2, not x1 minus x2. And at x is equal to 1 point, then this R matrix is proportional to 1 over T times P operator. This P operator is a permutation operator, or swap gate in quantum computation. So this feature is important since later we should build up nearest neighbor interaction out of this permutation operator. Without this property, we cannot build up nearest neighbor swing chain. And then since here we have Yang-Baxter equation satisfied by this combination, this means that the system or structure constructed out of this formula, its integrability is confirmed, is guaranteed. Then we perform the standard Yang-Baxter algebra procedure. Then the monodromy matrix can be defined in this way. So it's a series of R matrices, or in other words, it can also be like locked operators acting on either auxiliary space and also on a series of quantum spaces from N until 1. So the total monodromy matrix are a series of R matrices being multiplied together. And then from the auxiliary space 0, this total monodromy matrix can be divided into this 2x2 block. It's each element is a quantum operator among all the acting on the quantum spaces A, B, C, and D. And the Yang-Baxter algebra, the aim of Yang-Baxter algebra is to study the commutation relation among these four operators in a standard procedure. And since the R matrix satisfies the Yang-Baxter relation, and then it will lead to that the Yang-Baxter relation can be generalized to this monogeometry matrix. So we have RTT and TTR. So in this sense, we then can take partial trace on the auxiliary space on both sides. Then we conclude that the transfer matrix defined by trace over auxiliary space, which is capital A operator plus capital D operator. Such an operator with different spectral parameters commute with each other. So this confirms the integrability come out of such kind of constructions. So all the descendants that can be derived from this transfer matrix are quantum integrable. Then for our case, actually, we can obtain the Hamiltonian with the nearest neighbor interaction by calculating the logarithm derivative of the transfer matrix in this way. So here is some constant to get rid of the diagonal terms. Here, later I will show it in next frame. And then we have the local Hamiltonian expression. Here, this is just some formal expression. Here, the essential point is that here the partial logarithm derivative will give this local Hamiltonian density in terms of this permutation operator multiplied by the first order derivative of R matrix, which I written down here. So the logarithm of local R operator has this form. It's permutation multiplied by R, then take derivative with respect to X. And now it has this exotic form. Okay, then let's get rid of the diagonal term, like what we do globally by subtract identity to eliminate the diagonal term. By subtract identity, then we get the clearly projector matrix form as a local Hamiltonian. Then since we have this sigma plus sigma minus, so can be used to describe the off-diagonal terms. So this off-diagonal terms are just a simple expression, which is sigma plus j, sigma minus j plus 1, plus t times sigma minus j times sigma plus j plus 1. But for the diagonal elements, since they are not balanced, so this is kind of a little bit complicated. But we can observe from the expression that here for the single sigma z terms, for this sigma zj and sigma zj plus 1, they have minus sign as coefficients. So this will remind us that if we consider the global Hamiltonian, then such local terms, single local sigma z, will be cancelled with each other from another adjacent Hamiltonian local term. Means that another sigma zj plus 1 with minus sign with 1 minus t which comes from hj plus 1, j plus 2 will cancel this one. So this means that if we impose periodical boundary condition, this is some kind of global gauge transformation will balance the diagonal term. I will show you next frame. Then for this projector, if we want to be rigorous, then the corresponding projector has this normalized form. So this will make the square of this matrix return back to itself. And then after that, global gauge transformation, as I mentioned, I cancel this single sigma z term and impose the product boundary condition. Only in this case, then we can have this balanced diagonal term. And now, when we look at this matrix form, if we let t is equal to -1, then the diagonal term will cancel, become 0. And this means that this lower left corner become -1. This just recovers the Carroll XX chain with minus sign, which we mentioned before. So this is some kind of reduced deformation from the ASAP model. And such kind of reduction is quite similar to the XXZ spin chain model. For example, if we take the Hamiltonian of the XXZ spin chain, it has isotropic parameter delta on diagonal and 1 on the off diagonal term, just like this. And then if we take the free-forming limit, like the isotropic parameter delta tends to 0, then we will have the standard free-forming XX spin chain. So here in our case, this is just a similar reduction, looks like that one, but we have a chirality anti-symmetric form. And then from the standard ASAP model, the asymmetric simple exclusion percent, since it's Young-Box integrability, so we apply the standard Young-Box algebraic beta ansatz procedure. Then we have the corresponding beta ansatz equation and also the full energy spectrum of the whole system. So in this sense, we fully exactly solved the model completely. So on the other hand, we can directly consider the thermodynamic limit of the model. So we started from the original Hamiltonian. If we introduce the Jordan-Wegener transformation, and it will have this free-forming term with some boundary terms. Then in thermodynamic limit, these boundary terms can be ignored, can be thrown away. Then we introduce Fourier transformation. After the transformation, the Hamiltonian becomes diagonalized. Then we conclude that such a system is gapless in the thermodynamic limit. And from another point of view, we can also study the thermodynamic limit from here. Since we already have this beta ansatz equation and also energy spectrum, so we have the standard thermodynamic beta ansatz procedure, which was invented by Zhenning Yang and his brother Zhenping Yang. So that's the mainstream procedure for people who are doing thermodynamics from the point of view of quantum integrability and beta ansatz. So similarly, we have this gapless spectrum as a result. Here we show some numerical results of the spectrum gap of the system around G is equal to -1 and other parameter choices, which is for this frame, which is G is greater than -1. And for this frame, also this red curve for G is -1, and other curves are the other plots are the which for G is less than -1. So roughly speaking, at G is equal to -1 point, the spectral gap will smoothly decreasing as the total length size increasing, and eventually it will approach 0. But for the values of G away from this -1, such energy spectrum start oscillation. Later we should need more numerics to be done. Okay, now let's conclude my talk. So we introduced a kind of frustration-free spin chain, which composed of two projectors, and it has non-invertible symmetries. And we're mainly interested in the model with duality term. And at the special duality point J is equal to -1, the Hamiltonian of the model has a very strange pattern, which is similar to the alternating sign matrices in combinatorics. And also in this case, when J is equal to -1 duality, it can be mapped to the Carroll XX chain, and its integrability can be proved by means of Yang-Bakst integrability. Okay, that's all what I want to say for today's talk. Thank you.
Thanks, Professor. How for any questions? So is there any physical consequence of the non-invertible symmetries?
Physical constant.
Yeah.
Right now, we are working on the algebraic level. We haven't considered how to realize such kind of spin chain in real physical experiment. The main point is frustration-free and non-invertible. And also, maybe let me show you the construction. Maybe let me use this. Okay, so here, this is the basic setting of the matrix structure. So we have the same ratio of the columns and rows, means that the second row is A times the first row, and also the second column is A times the first column. Actually, we can choose different ratio among row and column. For example, we can choose B here, and here the lower right column will become A times B. And also, we can generalize such kind of structure to hierarchy. We can choose, for example, here for the 3x3 cases, then we can choose for the third row, we can have A squared, and then here A cube, and then A raised to the 4. And also, we can choose different ratio on the third row, like B. Okay. All such kind of generalizations are allowed.
So the A equal to A squared still satisfied if you have such extension.
Yeah, in that case, we should use different coefficient in the front to different normalization. Yeah. But we still should confirm it's a projector.
Your almost last slide, where you do the numeric dy when G is equal to -1. The energy gap approach 0 with the dynamic motion. It's not obvious.
Yeah.
It may become a symptotic to some.
Yeah. The point is from this free-forming expression that this diagonalized Hamiltonian. Yeah. But n
sign becomes
then n tends to infinity. This will compress the oscillation.
Yeah, but then if you have this analytic form, we don't really need numerical.
Yes, but we want to calibrate ourselves. At this g is equal to -1 case, we have this analytical, beautiful algebraic Betancourt expressions.
Your proposal is this AF model?
Yeah.
It kind of represents
Yeah.
it unifies these different models in different ways, right? The state.
Yeah, I think it's kind of new spin train model. Yeah, composed of such kind of projectors.
So applying your model to any quantum information on the computing system. Because we know the basic model is a basic model in quantum computing.
Yeah. We haven't realized this. Yeah, actually, we in recent years I have some collaboration work with Professor Vladimir Karpin and his former PhD student Kun Zhang, which he got his PhD in Stony Brook, and his main direction is quantum computing. And we try to realize like an Ising model and also some quantum integrable circuit on the IBM quantum computer, but yeah, we haven't considered this kind of structure. But yeah, we can try in the future. But the thing is that since right now, Kun Zhang has already returned back to China, we do not have the access to IBM Q anymore.
And I see the numerical also.
Yeah. One thing is here, and then another.
Yeah.
You want the first?
Yes.
Yeah. Okay.
You see when A is small,
Mhm.
then when A is larger, the gap becomes smaller. But when A is very large, then when Q is 130, then the gap returns to red. Is there any explanation that there is a minimal width of the gap? Or F equals 32, then it seems to almost gapless.
No. That's different. That's different meaning. No, gapless is not to say that. No, that's a different between a small number and an infinity small. Yeah. So it's different.
So the gap.
Yeah, never close.
So
Yeah.
what is the meaning? Yeah.
Yeah, I think you can choose different spectral parameter A and F, and let the gap become less and less and less, smaller and smaller, but it's not infinitesimal.
I think he was asking what's the lower bound.
My guess is it has no lower bound, but it's not infinitesimal. This is some mathematical meaning. Yeah.
When F equals 0, it is still gap.
If it's zero, then this will vanish. This model vanish, right? Sorry, I can't hear. As I said, right now we're working on the algebraic level. And of course, you can try to explain the physical from the expression here. We write the Hamiltonian in terms of Pauli matrices, right? And after the transformation, we have this chiral chain, chiral XX chain. Such chain should have physical meaning, right?
No more questions left. Thank Professor Howe again. 几点钟的飞机
1点20的。
那可能去食堂吃饭。5点40。